I'm requesting. Point out here that variance of sample equivalent to the variance of population divided by n. Also, we can say if we make a square root both sides, it is equivalent to standard deviation of sample equivalent to standard deviation of population divided by square n. Yes, you can see here as the n increase to unlimited, meaning that when we have a very large sample, this point will decrease, right? Going to, yeah, limit to the 0. When the limit is 0 means that this is close to here. The x bar close to mu x means that the x bar equivalent to mu x when the standard deviation of x bar equivalent to 0, something like that. Well, so one thing that you have to point out that when we have a very large sample, the sample average will close or equal to the sample populations, something like that. Okay, any questions? So the first finding, based on the central limit theorem, the sampling distribution of x bar tend to towards normality even when the population is not normal. Yeah. And then finding 2, the expected value x is mu, means that the sample average will be equal to the sample populations. Sample average will be equal to the population mean. This is the population mean. Finding 3, is this relative to the square root law, which say that this is the standard deviation of sample because of this one. This is the standard deviation of populations. The relationship is standard deviation of sample equal to standard deviation of population divided by square root of number of sample. Okay. Standard deviation of sample, yeah, this is the standard deviation of sample. Also, we can call as a standard error. Standard error, yeah, standard error, SA. Standard error. Standard error. What kind of error? Why we can call as an error? Because error, the meaning of error, or actually the error is because of the gap between the mu x and the x bar. This is the error. This is the error. So standard error represents also how close the sample average to the population mean, something like that. Yes. You can see here, this is just a proof. When you have a standard deviation of sample being 15, and sorry, this is a standard deviation of population, yeah, population, and given by only one number of sample, the standard error will be 15. When we have 4 number of sample, standard error decreasing become 1.5. And when the number of sample still increasing, let's say 16, the standard error keep decreasing, become 3.75. You can see as the number of sample increase, the number of the standard deviation of sample, or we can say a standard error, the standard error decrease. And you can see from this pattern, as we have a quadruple number of sample or sample size, the error decreasing, yeah, half, yeah, decreasing half. You can see here from 15 to be 7.5, it's half, and then become half again when we have 3.75. Yes. Also, when we have the sample being standard normal, meaning that the sample being normal, sorry, we can write being like this. This sample distribution being normally distributed. That's why we can write as n, and become the mean is equal to the population mean, and its variance, you can see here, this is the standard error, something like that. For example, let X represent an adult intelligence score, ICE, where the X is normally distributed with mean being 100 and standard, the variance being 15. Oh, no, not variance, but this is standard deviations, yeah, standard deviation. Okay. You can, for example, take an SRS. For example, you make some sampling for 10 students or 10 people. Yeah, 10 people. So we can easily compute for the standard deviation of sample being like this. Standard deviation population divided by square root of number of samples or sample size. You can see here 15, just simply write like this, and square root of 10. It is equivalent to 4.7. The 4.7 we can draw, let's say, being like this. Yeah, this is still 10, 100, but with standard deviation being 4.7. I will show you how the distribution look like. Sorry for a while. Think, NPF 0.1. Okay, seem a bit difficult using a MATLAB, so I will plot here. This is the, let's say, this is the N, the population distribution being mean 100.15, and for the sample, you can see here the mean is still same, but for the standard deviation is a bit smaller, so the graph looks like this, the blue one. The mu is equal to still 100, but the shape of the graph is different. You can see for the standard deviation 4.7, this is the blue one. Blue one is sharper than 15. Okay, that's all. Yeah, this is the ideal illustrations comparing between the population distribution, this one, and the sample distribution. You can see this is the standard error or standard deviation of sample being 4.7. Otherwise, the standard deviation of population being 15. Smaller standard deviation, the sharper this graph. The graph is more sharper than when we have a larger standard deviations. Okay. And then we want to know the area. Let's say we have, you remember, this is the 68, 95, and 99.7. This is a rough result. You remember that, let's say this is the population distribution, and this is the mu x, the mu x, and you remember this is, let's say, this point, this is first standard deviation, this is a standard deviation, and this is the twice standard deviations, also this is the twice, and this is the 3 times standard deviations. And also for this one, this is a 3 times standard deviations. Okay, you remember that this point and this point, this area, the blue one is around 68%, right? And the area of the red one, this is around 95%, right? And the yellow, okay. The yellow here, the yellow one is the size is 99.7%, right? And from this point, okay, for 68%, we can compute this point equal to the mu x minus standard deviation of sample, right? So it is 100 minus something like that. For this point is 100 plus 4.7, right? 104.7. This is for this. And for 90%, we can easily this point compute as twice of standard deviation. So start from 90.6 until this point is 109.4. And so on and so on. Yeah, for this point and this point. Okay. This is this in this slide also the another example of large number theory or law of large number. The mention that as a sample gets larger and larger, the X bar approach the mean populations. The figure demonstrates the result from an experiment conducted in a population with mean being 173.3. This point is, yeah, this point 173.3. The axis representing the number of sample or sample size. You can see as the sample size getting larger, the average will be saturated or steady state at some point. You can see here in this point. This is like a historical data. When you only have one sample, you will have a really get this point. After the second sample, maybe you will have this in this point. Third sample, this sample, this sample, this sample, and so on, so on, so on, so on, and the result, this is close to or converge to some number here. This is the proof or illustration proof that when we have a larger and larger sample size, you will have closer to the sample populations. Sorry, closer to the mean of population or population mean. And then we move forward to specific applications. We can say a sampling behavior of counts and proportions. For example, a binomial random variable represents the random number of successes in an independent Bernoulli trials, each with probability success being P, and we can notate or we can write the random variable X which follow the binomial random variable being like this. The N is the independent trial, the independent Bernoulli trial, and the P is the probability of success. For example, the binomial random variable given by the N equal to the 10 and the probability being 0.2 shown in the next slide. Note that mu, the mu is just result of multiplication 10 by 0.2 multiplication this one, and we have a result being m equal to be 2. Re-express the count of success as proportion of p hat. So we can say that the p hat probability of being success, we can say the x divided by n. For this expression, the mu equal to 0.2. This is the binomial distribution. You can see the y-axis, this is the probability. The probability, and x, the axis is the number of trial that success. The number of trial. And also representing the proportion or the probability of sample. And the mean of the binomial, this is just, you can see here, 2. This is the result of 10 multiplied by the proportion of probability being 0.2. It is equal to 2. Any questions so far?
No question.
No question. Okay. Okay. This is the population distribution. Population distribution. And then when we sample this distribution, when we sample distribution, let's say with sample size become n. Let's say n is large. The binomial distribution will approximate to a normal distribution. This called as the normal approximation. So from this statement, we can see that any original distribution, if we sample this distribution, we will have the normal distribution. So let's say this is the graph of any distribution. Any means that they can be binomial or can be a Pascal or exponential, begitu, something like that. And then when we sample this one, the result of the distribution will get the normal distribution. So that's why we can call as a normal approximations. How large does the sample have to be applied? The normal approximation. One rule say that the normal approximation when the n multiplied by probability of some random variable, and this is the complement of probability greater than or equal to 5. You can see here, let's say we have the sample size become 10. So if we have 10, we have to check or we have to compute based on the expression that P and PQ should be at least 5. And if we have 10, we just substitute here 10 multiplied by 0.2 and multiplied by 1 minus 0.2. And the result is 1.6. And then we can check, is that this distribution is normal? Actually, from this figure, we cannot say this is a normal distribution, because the left side, the left side and right side not really equal. Not equal. But if we increase the number of sample, let's say 100, so 100 will be 0.2 multiplied by 0.1 minus 0.2. The result will be 16. 16 is already greater than 5. And if you have sample being 100, the sample distribution will looks like a normal distribution like this. In case of binomial distribution, the mu will be as a result of multiplication between n and p, and for standard deviations will be square root of n, p, and q, multiply each other. When normally approximation, we will have the something like this. This one, this is the given as a mu, and this one is a standard deviations. And also similar, if we have a binomial proportion, means that the binomial in represent y-axis in probability. So given the binomial proportion, the distribution of sample will be, this is the p, and the mean is p, mean, and this is the standard deviations. It becomes square root of P and Q divided by N. This is the representing of the sample proportions. Actually, the y-axis, this is the probability. And the sample proportion, you can see this is a probability. But for this is the number of successful. Number of successful trial. Number of successful trial. But for this is proportion become success. This is the illustrative example of normal approximation from the binomial distributions. Suppose the prevalence of a risk factor in a population is 20%. Take an example of n equal to 100 from populations, and a variable number of cases in a sample will follow a binomial distributions with n equal to 20, and the proportion become 0.2. The normal approximation count, we can easily define that the mu is multiplication between the number of sample multiplied by the proportion. The sample mean proportion is being 10 100 multiplied by 0.2 and equal to 20. And for the standard deviation is equal to square root of sample size, the probability, and the complement probability, and then we can have 4. So the normal distribution of the count means that the successful trial, you can see here the normal distribution of 20. This is the mean, and this is the standard deviations. And for the normal approximation for the proportion is the mu equal to 0.2, actually equal to its proportion. And for standard deviations of the normal approximation will be the P and Q divided by n, and then being square root, and 0.04, and then we'll have this one. And the result is being like this. Actually, between the proportion and the distribution of count, the pattern is the same. You can see the pattern is same, but only different with in the x-axis. The proper count representing the number of success. This is looks like an integer, but for the proportion, the x-axis is in probability. Yes. Any questions from this sample?
No, sir.
No. Okay. Okay, this is another example. The problem, we have x become normally distributed with mean being 20 and standard deviation being 4. You have to note here, this is the distribution of populations. And then suppose we observe 5 cases in the sample. What is the probability of observing at least 30 cases under the circumstance? Which is the probability greater than or equal to 30? What is the probability observing at least 30 cases? So, the illustration is being like this. This is the population of this is the distribution of populations. This is 20, something like that. And then you make some sample, at least 30 sample. 30 sample. This is a 30 sample. Let's say like this. I prefer to different color. This is the sample distribution. And then you order to compute the probability. Let's say this is 30, 30, and I make a point here with the full fill of 0. You have to find the probability case at least 30 case, yeah. So in this point, you have to find the size of the green area. The green area. How much the size? It is equivalent to this one. You can see the probability x, where the x, because at least 30, we have to include the 30. So that's why the greater than or equal, you see here the equal to 30. Okay. Okay. I hope it is clear. Any question by illustrating this problem into this graph? No questions? Okay, if no, we next. Actually, from this point, you can find the probability from the integral, or using table, or using what? Using the calculator or software. And from the table, we will have the equal to the probability is being 0.0062. 62. Actually, this is by table. We have to find or to compute the standard normal variable z. Z equal to 30 minus 20 divided by 4 is equal to 2.5. 2.5 based on the table will be equal to the probability is 0.0062. Okay, this area is 0.0062. Yeah, so we arrive at this. What is the probability of serving at least 30 case? Yeah. So we arrive at this point. Very small. Yeah. Okay, if I have a question, let's say this is the exercise. The exercise, that is number 1, find the probability, let's say probability x greater than 19, and second, the probability of 20 x 30. Okay, anyone can compute this one? Please try by yourself. And the second one. Okay. Actually, very easy. To those who can conduct or compute this result, I will give you bonus 5 point for the UTS. I did to the UTS. I did to the middle exam. Also for the number 2, also I will give you 5 score addition to add up your middle exam. Please try. Maybe I give you 15 minutes. Are you there?
Yes.
Okay.
Yes, sir.
Yes. Okay, please try. Write your name in chat box to those who want to answer the question. Number 1 and number 2. I will only pick the person who already mentioned the name.
Sir,
Yes.
I want to ask a question.
Yes. Yes.
For the probability of Z more than 2.5, where do we get the answer? 0.0062.
You mean this one to this one?
Yes. Is it by looking at the table or
Yeah.
what?
It's up to you. Using table or using software calculator or using integration is up to you.
What is the table's name, sir?
The table? The
Yes,
table's
the
name?
table's name for
Yeah.
Z.
The
Yes.
table's name is
Is it
standard.
distribution table?
Yeah, standard normal distribution table.
Oh, okay, sir.
Yes.
Okay, thank you.
Okay. Puluh 30. Okay, okay. And then X lebih besar 19, P 20, X 30. Oke. Oke. This one. Okay, to those who want to explain the answer, maybe what do you mean, Sanditya? What do you mean for your answer?
Sorry, sir.
Yeah, you answering the.
Oh yeah, that's
percentile X. You asking?
Yeah, sir. I misclicked, sir. So I was actually writing on another notepad and I miscopy.
Okay.
Yeah.
Okay.
Yeah.
So okay. Maybe the first one maybe for Nadia Mayesa.
Yes, sir. Present.
Yes, please answer for the probability X greater than or equal to 19. How do you compute using?
Well, I'll be honest, sir. I used the calculator online.
Okay.
So I put in the mean as 20 and the standard deviation as a 4, and then I executed the program and received the.
Okay. Can you explain in this board here using annotation, for example? Yes, I expect that not only you understand, but for others also can learn from your answer. Yes.
I don't really know how to explain it, sir.
Yeah, but actually, you not directly find the answer, right? But you should compute step by step, right?
No, I actually used it. I found the answer directly, sir. I didn't use step by step.
Okay, if you answer directly, please show me how to answer or how to compute even using calculator. You can share maybe the calculator that you use.
Okay, sir, hang on. Can you see my screen, sir?
Not yet. Okay. Right now
Yeah,
it's
so
processing.
I use this app basically.
Yes. Okay, please explain.
Okay, so from the question, I've put in a percentile x of 19 and a mean of 20 and the standard deviation of 4. And I got the results of 0. For the probability density, I got a result value of 0.096 recurring. And then for the lower cumulative, I got a 0.401. And the upper cumulative, I finally got a 0.5987. And if I were to manually calculate it, I would use this equation, but I went for the fast route.
So the answer is which one?
Upper cumulative Q, is it, sir? Please correct me if I'm
Upper
wrong.
cumulative Q, okay. Okay. Okay, yeah, seems to be correct. Thank you.
Thank you, sir.
Okay, the next question is maybe for different answer is Ervigo Smaradeva for the number 2, please.
I already calculated for number 1 only, sir, but the number 2 I haven't yet calculated. So I need more time to calculate.
Oh, for number 2?
Yes, I only calculate for number 1, sir.
Oh, number 1, okay. Goldie, you are answering for number 2?
Yes, sir.
Yes, please, and explain.
I calculate the same with Nadia using calculator.
Yeah, no problem. Please explain.
The middle probability between 20 and 30, and for solving the problem, I input less than 30 and less than 20. Only like that, sir.
Yeah.
But I'm not sure for the my answer.
Yeah, you have to be sure. So that's why you have to share screen, please.
Wait.
Yeah.
Sir?
Yes.
Maybe can I try for number 2? Or do you want to wait for Goldie first?
Goldie is trying? Preparing?
No, sir.
No?
I've already closed the tab, so I want to restart my calculator.
Oh, okay. 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 If Goldie doesn't want to show, and then please Ervigo. Explain to me.
So basically, the interval is from 20 to x to 30. And
yes.
Here I calculated the z first based on the table here. So the z here is 20 minus 20 per 4 based uh, on the z calculation z formula from standard deviation minus the mean and per 4 as the standard deviation. So the z here is 0, and I calculated for the interval is 20 to x to 30. So the probability for x being larger than 20 is 1 minus x being less than 20. So the calculation here is the probability is 0.5 for the 1 minus x less than 20, and for the x minus please wait. So for the x less than 30, here is I calculated the z2 for the 30. So the z here is 30 minus 20 per 4, which is the same from the example. Here is 2.5. So if you look at the table here, if z is 2.5, here 2.5, 0.993. Here the probability is 0.993 for less than 30. So this is the probability 0.993 and 9983. And for the 20, the interval is 20 less than x less than 30, less same than x and less same than 30. So if we calculated the z for the 20, here I already calculated the z for the 30, and the second one I calculated the z for the 20, which is 20 minus 20 per 4. Here it's 0, I think, the z. And based on the table here, if z equal to 0, the probability here is 0.5, which is mean it's less than the value in the 0.5 in less than 20. So the probability of x less than 20 is 0.5. And if I calculate it for x more than 20, it should be 0.52, right? Since 1 minus 0.5 is 0.5. And the probability, I think it's 0.4. I think it's 0.
So the answer is
0.4983, I think so.
0.4983.
83.
83. Okay, let's check it together. Yeah. So your answer is okay. Your answer is, where is it? Okay. 0.4
4983.
930
80. Oh, huh? Let me write it down in the chat. 4983.
82. Okay, sorry.
Yes, I already wrote it in the chat box.
82, something like that, right?
Yes.
Okay. Okay, let's check it together. The problem is probability. Find the probability x greater than 20 and less than 30, right? Okay.
Yes.
So this is in x variable, but if we write in z variable, this point and this point, okay, starting this point, what is the number here?
0. I calculated 0. 0, I think.
0. Okay, good. And this one?
2.5.
2.5. Okay. Okay. This, if you if you want to calculate using integrations is equal to 0 to 25. This is the PDF being the mean is 20 and for this one and dx, or equal to the probability. Using another way, this is probability probability, yeah, z greater than 0 minus probability z greater than 5, right? If we want to draw this one, something like this is 0, and this one greater than, and this one is, I feel this one means that the 0 include, but in this point 2.5 it doesn't include. Okay. Oh no. No need this one. I will write this one. Okay, this is minus. This is probability for this one. This is 2.5, but this one, right? Yes. So the result will be probability equal to something like this. This is 0, this is 2.5, and 2.5, this is include. This is equal to this one, right? Okay, let's find together. For this one, actually using the calculator, but if I change the calculator, Siemens. Compute normal distribution online and the Keysan. Okay. Okay. Sniff. Okay, good. Okay, stop share, and then I will change to this one. Okay, I hope you can see here. So it's 2 0, yeah, 0 0. So right here 0, and just execute. Actually, this one and this one. This one is 2. I already share, right? Share screen, okay. Yeah, we already shared screen, so the result is being like this, and we got the 0.5. Okay. So the probability of PZ greater than or equal to 0, it is simply we can write 5. Okay, good. And then we want to compute the probability Z greater than 2.5, right? Greater than 2.5. So it is equal to the probability 1, probability Z, right? 2.5, right? Okay, something like that. So this one is minus this one. We will pick up this one, but first I will change the 2.5 here. 2.5, right? Less than, yeah. Okay. Okay. 2.5. 2.5 is the here. I'll write 0.993 but 79, right? Because of 79 we round it up, so it's like 0.993 8, right? Okay. And back to the problem, the final computation, we have to find this expression, right? 0 greater than 0, and then probability 0 greater than 2.5. Yes, yes. This one is 0.5. Yes, minus 1 minus 0.993, right? Okay. Okay, I hope you got it. And this is a 0.5. Minus or equal to plus this one, 9938 minus 1. So the result is 0.4938. Okay. Okay, this is the result. The final result of given the problem is 20x with the mu equal to 20 and standard deviation equal to 4. Any question? Do you have any question? Is that clear? If not
Clear,
clear,
sir.
yeah. If not clear, please which one or which the area that is not clear.
It's clear for me, sir.
Not clear. Okay, good. Yeah. Okay, bro. Okay. The next is I want to summarize about the estimation parameter. Yeah, I want to summarize about the estimation parameter. Yeah. Okay, which one? Okay. No, and then okay. The summary will be delivered in the slide is in bahasa. Yeah. But actually, this one I will explain the estimation parameter. Yeah, estimation parameter means that estimate the parameter in the populations. Yeah. What is the parameter in the populations? You already know. We can say it is a mean or its variance. Yeah, the mean population and the variance populations. Okay. Okay. How to estimate based on the number of sample size? Yeah, based on the number of sample size, we can typically say as estimation point or estimation point or estimation interval or interval estimator. Yeah, point estimator, something like that. And then first, how to estimate the point or point estimator? Yeah. As you know that the point that we are talking about is the mean or equal to the expected value. Yeah. Another name of mean of population is expected value, and also the standard deviation of populations from the sample. Okay, first is how to estimate the expected value. How to find from the sample average to be closer to the expected value. Actually, yeah, you can see here, this is the error. Yeah, the error between the sample average and the expected value. There is a gap, there is an error. Yeah, there is some point. Yeah, that we can say is a error. Yeah. I already mentioned that this error will be equal to the variance of sample. Yeah, variance of sample, and the variance of sample is equal to the variance of populations divided by the number of sample. Also, it is equivalent to standard deviation. Yeah, this is the variance expression, and this is the standard deviation. Actually, this is the standard deviation of sample, and this is the standard deviation of populations. Yeah, population divided by square root of number of sample. Yeah, or sample size. And then after we estimate the expected value, and then we can estimate the variance or estimate this one or standard deviations. Let's say to find the variance, given that the variance of population is, we can express being like this. And from this expression, we can divide into two conditions. There is two conditions, means that the sample mean is known. And the second condition is sample mean is not known. For the case, the population mean is known. Sorry, this is the population mean. The population mean is known. In a very special case, it is like a noise. Noise has mean become 0. Because of 0, we can substitute here 0. So the final expression is being like this, because of 0. The final expression is being like this. So we can easily define that the variance of population is just expressed like this. Otherwise, when we don't know about the population mean is not known, and then we can just simply say that the population mean equal to the sample average when we have a large number of sample, or we have a sample size is really large. Another method is interval estimator. Yeah, interval estimator. The interval estimator is a kind of method to find some parameter that falls in certain area. For example, we have a population mean, let's say, become 20. Okay, become 20. And then you make a sampling, let's say maybe 10 sample. 10 sample, and you got the sample average being 21. Become 21. And I am asking you, about your sample average. How much you believe that your sample average is reflected to the sample to the mean populations? How much believe? 60%? 90%? Or 100%? That's the questions. How much believe that the 21 is the same population mean from your sample? Maybe another person, maybe your friend take the sample 100 sample, and he got the standard deviation, the sample average being maybe 20.5. And then I'm asking, how much you believe that 20.5, this is reflect the population mean? Because we are talking about the belief. How much the belief? That's why we define a range or interval. Range of or interval. Usually, the meaning of belief reflecting this area. Sorry. Alhamdulillah. This is the C, let's say minus C, and this is the positive C, given by this limits. If the sample, for example, we have 90%. So by 90%, then we can define the C. And then once we know the C, and then we can have the interval, positive C or negative C. Okay. After we know the interval, and then we have you have to check that the sample average inside of this range or outside of this range. If the sample interval inside of this range means that your sample average is correct with 90% of belief. Otherwise, if your sample average outside of this interval means that your sample is not correct. Because of not correct, no need to be belief. Something like that. Any question? Any question, bro? Is it hard to be understood? Any questions? There is a method to find these limits. Sorry, negative C and positive C. This limit. First, using Markov inequality. And the second, using Chebyshev inequality. Once you get this Chebyshev inequality, you can easily define the C here. And this is another example using Bernoulli distributions. Okay, for example, given the sample for American president elections and US president election, given the sample, the sample size is 1,130 people. The percentage of supporting Trump being 58%, with the accuracy being plus minus 3%. And then compute how many percent that the US citizen will support Trump. Given that the number of sample size being 1,103%, and the sample average being 0.58, and the C is 0.03. The MX, this is the population's mean, becomes 0.5. That because every person has a probability being select support Trump or not support Trump. Support Trump means that 1, and not support him become 0. That's why every person has a mean become 0.5, something like that. And the question is, how many percent? How many the probability that the US citizen will support the Trump? Mathematically, will express being like this: 1 minus the alpha, which the minus alpha, it is equivalent to minus variance x. This is the n, the number of sample size, and this is the c power by 2. And because of only 2 candidates, then the distribution model we use the Bernoulli, where the variance of x will be equal to this expression. This is very special case for the variance using Bernoulli distributions. P multiplied by minus P equal to 0.25, because the P itself is 0.5, yes. And then 1 minus alpha, we can easily compute using this one. And we got the alpha is 0.2518. And then 1 minus alpha become 0.7482, or equivalent to 74.82%. This is another example. For example, a signal is sent it. The signal we can write as a B, and then after pass through the transmission channel, the signal added by noise. Yeah, noise. That the noise is followed by normally distributed. Noise is normally distributed, so mathematically become like this. This is the signal received at the receiver, the X, E, and B, this is the signal transmitted from the transmitter, and Z, this is the noise random variable or noise parameter. And then the distributed of noise, noise distribution has a sample mean of noise is become 0, and the variance of noise is 1 watt. And the question is, how many sample need to be taken so that the signal is between this point. Minimum is not minimum, but greater this point and less than this point, with the belief is 99%, and the tolerance that given is C 0.1 watt. Okay, the illustration is being like this. The question is, how many sample here? How many sample? And the requirement is you have to believe until 90%. So graphically, first, because the noise is normally distributed, so the graph is like this. Yeah, the graph is like this. Okay, then the B is become the mean of signal. Yeah, B is located here. Why is located here? Because the B is constant. The signal of the power of the signal is constant. Yeah. And then the orange one is the uncertainty. Uncertainty is simply 0.005. Yeah, and also this one also is 0.005, right? Any questions? Yeah, because the we have to know that the total under the graph it should be 1, because we already defined that the white area it should be 0.99, so the other area it should be like this. Okay, the expected value is a B, actually the mean, and for the variance is 1 watt. It is depend on the variance of the noise, and then the equation will be like this: the probability that the B is between this one equal to this one. Actually, we can easily, let's say, the X minus C greater than B, right? It is just replacement, right? This one is put here, so the Mn X minus B C, right? Yes, something like so. This one is put here. Okay. And then you know that this expression is equal to less than or equal to 1 minus variance x divided by n. So we can easily rewrite this expression also equal to the upper one, and then minus 1 minus variance x divided n c power by 2, and then this area, actually this area is 99.99. This reflect this the white one, okay, and then less than 1 minus 1.n 0.1 power by 2, and then we can get the number of sample. At least you have to take an example or take sample at least 10,000 sample, something like that. Okay, any questions? No? Yes? No? Please? Okay, this is another example. You can read by yourself. Okay, we finished our class today, and I plan for having an assignment for this week. Please check regularly the mass, or maybe I will let you know from WhatsApp for the assignment that you have to conduct. Okay. If you don't have a question,